Hello students. So let's continue with unit 1. So agenda of today is learning about the fundamentals of control systems. So you have to know what is meant by control systems. So we'll see what are the different concepts used in control systems, and we'll see the basics of control systems today. So this is the vision of two great concepts. One is IoT and the other is CPS systems. So the two concepts originates from two different communities. So, considering the engineering aspects which drive CPS and it concentrates on the physical systems behind. So, CPS is driven by engineering aspects and it concentrates on the physical system. So, which should start to communicate and cooperate with each other. So, considering this, the difference may be like a huge difference in which the methods applied will make us understand the upcoming systems, which they can lead to different modeling, controlling, and steering paradigms. So, traditionally, we have CPS systems that has been engineer driven. So, that has been driven by engineering, which emphasizes on physical system control. So embedded systems managing sensors, actuators, and mechanical components can be considered in a closed loop system. So in IoT, it is driven by computer science and internet technologies. It also understands itself as an extension of the internet concept, and it focuses on openness and networks. So this is the basic idea of control system. So next we'll see what is meant by control system. So you should get the basic idea of a control system. So control system is nothing but is a set of devices or algorithms. So which controls some other systems based on its behavior, and it can manage, it can command, and it can direct or regulate the behavior to other systems to achieve a desired output. So it operates on input, process, output, and we call that principle as IPO principle. So it's very easy. So control system is nothing but it's a system which can control the other systems to achieve a desired output. So basically you have to understand this is the concept of a control system. So control system refers to engineered systems whose operations are integrated, monitored, and are controlled by a computational core. So here we'll move on to the types of control systems. So there are 6 types of control systems. So we'll see one by one. So the 6 types are specified in the left hand side. So open loop system, closed loop system, we'll be learning about SISO, MIMO, continuous time systems, and discrete time systems. So first let's consider open loop system. So here there is no feedback. So output does not compare with the input, and here for example we can consider a toaster. And moving on to the closed loop system. So it uses feedback to adjust input based on output. So here we can consider an example as cruise control. And moving on to the next control system, we have SISO. So it means that single input, single output system. And next MIMO, it's nothing but multiple inputs, multiple output systems. And the next type of control system, we call it as continuous time systems. Signals vary continuously over time. And we have discrete time systems. Signals are sampled at intervals. So when you consider these type of control systems, these control systems are often modeled using different systems. First, we can see it can be modeled by differential equations for continuous systems, and it can it can also use Laplace domain, so that we call it as transfer functions. And state space models can also be used for modern control theory. So here basically in control systems, we have some analysis techniques. So we'll see what are the analysis techniques here. So first we can see time domain analysis. So when you consider time domain analysis, it focuses on system response over time. So basically For example, setting time, rise in temperature, etc., can be considered here. Frequency domain analysis is the second type of analysis technique. So it uses tools like board plots, diagrams to study system behavior. So next type of analysis we have stability analysis. So here this learns about, or it determines about the system which will remain bounded over time. So these are the three analysis techniques. So you have to understand this concept. So first we have learned about time domain analysis. The second we have learned about frequency domain analysis. And the third we have learned about stability analysis. So these three techniques are really very important when comes under control system. So next we'll move on to controller types and its functionality. So the first controller type we have P, which is represented for proportional. So it adjusts output proportionally to error. So that's the functionality of this particular controller. And the second type of controller we call it as PI, that is proportional integral. So it eliminates steady state error. And next type we call it as PID, proportional integral derivative. So the functionality of this PID is it combines speed, accuracy, and stability. So here in these types of systems, we use some tuning methods. So we have some tuning methods. So I'll just tell you what are the tuning methods we are going to use for these particular systems. So Ziegler-Nichols, that is the first type of tuning methods. So this particular method is used for empirical method using system response. And the second type of tuning method we call it as Cohen-Kuhn. So that we call it as a process reaction curve. So it is based on process reaction curve. And the third we call it as manual tuning. So it is based on trial and error, which is often used in practice. And next we have optimization based tuning methods. So it uses some algorithms like PSO or IFRSA, for adaptive tuning, etc. So these are the basic tuning methods used for system design. And next we are going to learn about control system. Basically we are going to see it in cyber physical systems. So CPS are defined as engineered systems that are built from, and it depends upon the seamless integration of computational algorithms and physical components. So here you should know about these particular systems. So computing is deeply embedded into every physical component, possibly even into materials. So the computational core is an embedded system. So usually demands real-time response, and it is most often distributed. So they represent the intersection of the physical world and cyberspace. So it is interdisciplinary in nature. So control systems within CPS or within industrial IoT framework involve an interdisciplinary blend of production, and it combines computer science, mechatronics, communication technology, and other technologies, and so on. So these are the basics of control system. So next we'll see about the key components of control system, right? So these are all the basics of IoT. So once again, I'll tell you the key components of control systems. So first is sensors, and the second we have controllers. So basically learning about sensors. So sensors are used to detect physical parameters like temperature, pressure, and so on, and it converts them into electrical signals, right? And so what is the use of controller? So it processes the signal and generates a control action, right? And so based on the key components, we have three key components. One is sensors, the second is controllers, and the third we call it as actuators. So all these key components you have learned in IoT itself. So we'll see in detail about sensors. So the output can be provided regularly, or it can be generated event based. For example, when a predefined threshold is exceeded. And based on controllers, controllers receive measurements from sensors, process this data, and generate output values or commands. So these commands are sent to the actuators. So in industrial automation, programmable logic controllers are often centrally collect input from various sensors and it control different actuators. And moving on to the next part, so I told you the next key component is actuators. So actuators execute commands received from a controller. So some action is triggered here, so directly influencing the physical environment. So within a CPU system, the computational core is an embedded system. So that is deeply integrated into a very physical, into every physical component, possibly even into materials. So considering this actuators, controllers regularly receive measurements from sensors as input. So the measurements are stored, processed, and continually fed into a control function, and mapping all these measurements to an output value can be considered here. So for example, we can say using a differential equation, so the output value is then sent as a command to one or more actuators. So what will actuators do? Actuators act upon commands received from a controller. So possible actions are moving a machine part to a certain position, or changing the rotation speed. For example, changing the rotation speed of an engine shaft or performing an emergency stop operation. So, considering more about actuators, they directly influence the environments in which they operate, right? So, it usually demands real-time response, and it is most often distributed. So when you consider CPS systems, so where virtual and real-time systems are linked closely at various levels, and the components are networked at every scale. So this is the challenge here. So as an intellectual change challenge, sorry, CPS system is about the intersection of both physical world and the cyber space. So moving on to the next part, control loops and real-time requirements. So here you will be learning about what is meant by control loop systems. So CPUs are often designed as closed loop systems where physical systems are closely linked with virtual systems at various levels. So it also emphasizes feedback loops for self-optimizing and robust behavior. So, moving on to the definition of real-time aspects, we can consider real-time traffic as an upper bound or a deadline on information delivery delay. So, basically, in communication for cyber physical systems, so it incorporates different control systems. So the time delay in the control loops of these systems has a significant impact on controlling the performance. So here system stability is a key control performance parameter, and it also depends on the response time of the system. So it can also be defined as the maximum time allowed between the occurrence of an event and applying the corresponding reaction. So here we consider the hard real-time systems and soft real-time systems. So missing the deadline for information delivery will mark the information as useless or negatively impact system operation correctness. So this is critical for application like plant control systems, sensors, and actuators. So in a control loop, the closed system uses a communication network. So then this will entail performance degradation or even destabilization of the systems due to the presence of time delay and other communication deficiencies. So in this context, The traffic of CPS systems, even between their units, is usually characterized as a real-time systems. So second, we move on to soft real-time systems. So missing the deadline will degrade the performance efficiency. So without considering the operation and its correctness. So this applies to less critical applications. So so here, depending on the effect of the deadline violation on the control system, it can be either considered as soft or hard. If missing the deadline, it will mark the late information as useless or even negatively, or it negatively impacts the correct system operation. So if in other case, we can consider the late information will degrade performance efficiency of the system, so its operation correctness, and it can be classified to be soft real-time systems or hard real-time systems. So based on real-time performance, so ensuring real-time feedback for effective interaction between computation and physical processes is critical here. So in real-time control, the computation is based on software needs, so that is aligned with the time lapse in the physical world. So, um, so here we can use some suitable programming languages and concurrent software that are not readily available. So if the computation is expected to provide real-time feedback for effective interaction. So the bit yeah. So between the computation and the physical process, there should be some effective feedback. So however, we can consider no such programming language and concurrent softwares are available for this purpose. So when designing a cyber manufacturing system for any operation, it is important to ensure real-time control for each manufacturing step. So with the network and its versatile features of cyber security systems, this challenge can be even more difficult to address. So it is still unclear to what degree real-time requirements, high speed, high transmission speeds, and low response times are necessary. So these affect the real-time performance in the system. And moving on to the next part, we can consider intelligence and autonomy in control. So autonomy is nothing but autonomous systems have the ability to make choice uh, free of human influence. So this moves beyond the programmed automation to systems that can design what to do next. So it has some designing algorithms. So it is not based on human influence, right? That you have to understand. Uh, so it comes under autonomous system. So next, moving on to self-X capabilities. CPS are characterized by self-X capabilities. So it represents self-description, increased adaptability, and significantly it increases local intelligence. So when you consider industry sector, many industry sectors have achieved a high degree of automation in production processes. So based on the automatic systems, it will do exactly as it has programmed and they have no other choice. So it will execute or it will do what it has programmed, right? So autonomous systems, however, have a choice to make free of outside influence. So this means in particular that they need to make some choices themselves without any human intervention, right? In a CPS system, in a smart factory, it should achieve achieve major steps. Uh, the capabilities has to be provided with software components, and it is necessary to provide system intelligence and autonomy. So it means that it is based on the software driven methods to analyze incoming sensor information. So designing on all these tasks and goals to accomplish, and it should execute the determined actions, right? It is focused on decision making, execution of components, with a primary example of multi-robot system in a smart factory logistics. We can consider components. So we have outlined the components necessary to achieve autonomy and represented three different use cases, or we can use a number of use cases here with several levels of sophistication and evaluation results, so that can be implemented to control autonomous robots. We can consider so many use cases, and we can see the sophistication and evaluation results on each particular strategies. So moving on to the next part, we have intelligence and autonomy in control. So basically we see three parts here. Moving on to the next, we have yeah. Yeah. Communication and networking for control. So network systems has to be considered. So CPS systems are inherently network systems. Um, we see some model-based engineering for control systems. So importance of modeling is considered here. Engineering complex CPS systems strongly depends on the proper application of model-based systems engineering. So this allows a formalized approach to specify the entire system and its behavior and its structure. So engineering such complex CPS systems has re-energized the field of systems engineering, which has been moving steadily away from a document-based practice to a model-based discipline. So in fact, success in cyber physical systems engineering strongly depends on proper application of model-based systems engineering. So model-based design and development of production and manufacturing systems is a crucial task, and it has been researched for many years. So uh, with the rise of new challenges in CPS systems, nowadays established models and methods cover different engineering and software aspects and often impose an early separation between these aspects. Thereby, modeling refers to a formalized approach facilitating the specification of the whole system or parts of its behavior as well as its structure. Modeling concepts contain several modeling tools, and these tools exist from both disciplines, engineering uh, as well as from computer science. So, in the context of CPS and CMS, it is necessary to bring these solutions together to achieve a formalized approach. So, next, it's based on control system development workflow. So it's based on hybrid automata models. Develop models of physical system components can be done. Uncontrolled hybrid plan to describe all possible behaviors are considered. So based on these particular behaviors, the workflow is proposed. So to start with the hybrid automata models of physical system components, they have developed so many components, and we can call that as uncontrolled hybrid plant. These models describe all possible behaviors. So the components can exhibit different specific system functions, and it has some restricted functionalities also. So simulation and simulation based visualization can be enabled. So this particular simulation based visualization can be performed by using an image model of the system, and it can be used to validate these models. So next we have discrete event abstraction. So this is considered to be a hybrid models. So from the uncontrolled hybrid plant, the uncontrolled discrete event plan can be abstracted. So with the help of hybrid observer that abstracts information. The discrete event abstraction is nothing but abstract these hybrid models into discrete event models. So based on model-based engineering of supervisory controllers, we have sensors and feedback controllers based on different types of events. So these models are expressed in terms of extended finite automata. So considering all these models, the models have some requirements. So with the requirements can be related to the functions of the system, and it can be defined in terms of extended finite automata or state-based expressions. So, based on the uncontrolled discrete event planned models and the requirements, the supervisory controller is synthesized using algorithms. So, from the area of supervisory control theory, these particular algorithms are used, and this particular supervisor can have a tool. We call it a CIF tool set. So this creates a discrete event model of the uncontrolled system. So this means that the hybrid plant, which has been introduced above all these particular descriptions, have abstracted into a discrete event model. So this is achieved by removing all continuous variables. So all these declarations are removed, and the differential equations in which their evolution over time is also defined. So in some cases, the evolution over time is defined, and in some cases it can be removed, and all the updates in which they appear on the left hand side are also considered to be in the left hand side. All the updates are also removed, and all parts of the gods in which they are evaluated are replaced as true. For example, we can say the discrete event automation which is obtained for the battery sensor can be predicted by using these types of discrete event abstraction. So next we move to control system development workflow. So here basically you will be learning about requirements definition, supervisory controller synthesis, validation and verification, and then we move on to benefits. So considering requirements definition, so it define system requirements using extended finite automata or state-based expressions. So as I told you, the uncontrolled discrete event plan can be abstracted, possibly with the help of a hybrid observer that abstracts information. So here, a model-based engineering of supervisory controllers from each sensors and feedback controllers by events are considered. So these models are expressed in terms of extended finite automata. So so I told you, so these models have some requirements. So the models of requirements are considered, and it is related to the function the system should fulfill, and it can be defined in terms of extended finite automata or state-based expressions. So moving on to supervisory controller synthesis. So it automatically generates the supervisory controller based on the discrete event, plant model, and requirements. So a supervisor is synthesized for a system consisting of two multi-movers. So here we can consider supervisor control theory, so which defines the construction of a model. So it's based on supervisory controller based on discrete event model of the plant and the requirements. So the resulting supervisor not only satisfies the requirements, but also it satisfies these following properties. First, we can consider the control system uh, can be considered as plant and supervisor together, which is not blocking. So a system is considered non-blocking when from each reachable state, and it can be considered as a marked state, right? And moving on to the third part, we have validation and verification. So it uses some simulation based visualization to validate the supervisor's functionality. Considering the efficiency and completeness, so some induction based verification method working on various levels can be proposed for generating models, making the approach complete, and it can be more efficient. So for this, for different systems, we call it a system CTLM designs, we report the verification properties describing the important behavior, so which cannot be used in various experiments. So considering this type of system, system CTLM, which designs, we report the verification of properties describing important behavior at TLM, which has not been possible before. So, moreover, considering all these experiments which demonstrate complete proofs can be carried out efficiently using induction. So next we have benefits. So this workflow shifts from manual controller development to declarative modeling, making it easier to adapt to changing requirements. So considering this workflow, so shift from manual controller development to declarative modeling makes it easier to adapt changing requirements. So additionally, we use some controllers like supervisory controller. So this particular model can be used for model-based testing, so which can be used to generate various test cases to which the real-time implementation can be subjected. So the important advantages of using these proposed workflow uh, are mm, basically by developing supervisory controllers to declarative modeling of the requirements, so that is able to provide changing requirements which happens in any realistic industrial case, and it is relatively very easy. So the effort is put in modeling and the system components. So all the requirements and the corresponding supervisor expressed automata is generated. So these models on the supervisory controller, which is obtained by the synthesis, can be analyzed by means of simulation, and this simulation process is very important, and the simulation along with the verification before being implemented, which also increases confidence and the correctness of the developed controllers. So this way the working can be used for generation of supervisors for equipment, transport, automated guided vehicles, etc. So next we are moving to the challenges in implementing control systems. So we have complexity management. So CPS and IIoT are complex systems of systems. So managing this complexity requires intelligent support and often involves the orchestration of dynamic manufacturing systems. So generally, when we consider CMS systems or IIoT systems or CPS systems, it can be regarded as complex systems of systems. So hence there is not just one technological basis to build such systems. So which can also result in various challenges. The technological basis and along with suitable architectures can be considered for the growth of complexity management. In further major challenges is based on the specification. Extensible infrastructure or architectural pattern can also be supported on one hand, and variety of sensors, actuators, and other hardware and software systems can also be handled along with the complexity of the system that has to be remain manageable. So even when you are using so many different types of systems and variety of sensors, actuators, and other hardware and software, complexity has to be manageable. So such a network system contains on a small scale such a network system contains on a small scale a scalar device, but it can also be manageable based on planning systems that give access to enterprise information. So example, highly aggregated key performance indicators and equipment effectiveness and bulk information like stock of components, parts and products are considered here. And the performance indicators are overall equipped with all these types of information. So in order to manage the various systems to provide a way, so we used to satisfy the information demands. So researchers as well as industrial uh, people have introduced several pseudo standard architectural systems patterns in the previous methodologies. So in the field of automation, the well-known automation pyramid or the more advanced automation representation can be considered to represent or satisfy new architectural patterns. So with the induction of CMS and IIoT in automation, these well-structured and task-oriented patterns can be resolved. So the classical automation pyramid will be gradually replaced with networks, decentralized, organized networks, services, and semi or automated services. So next, moving on to the data quality and inconsistencies. Achieving effective control is often hindered by inconsistent and incorrect data. So in order to improve the data quality, inconsistencies in the returned production of data can be automatically completed. So repaired by the use of probability functions. So it can show the influence of inconsistent data, so that can run on systems, and it can provide simulations also. So we have two types of simulations. So in the first run, it is assumed that the available data is fully consistent, and it can be considered as the results of the simulations are being compared to the results of the second simulation. So in which the failure of machine is being simulated. So in this way, the influence of data and its inconsistencies can be determined, and there is various set of control variables in the control circuit. So it can also be determined by various data inconsistencies, and considering the data quality and other inconsistencies, we have incorrect data from various IT systems. So automatic correction mechanisms are also needed to improve the data quality. So as I told you, there are two types of simulations. So we have in the first one, we'll be considering the data that is available. So after the first one, the results of the simulations are being compared to the results of a second simulation. So likewise, the varying data quality and and its inconsistencies can be rectified. So next, moving on to the cyber security and privacy. So here we'll be using decentralized and adaptive networks. So it protects data, and we can come to know how it can be guarded against external attacks. So, decentralized and adaptive systems are used here. So, you should know what is meant by this and decentralized and adaptive systems. So, it's nothing but blockchain based platforms for computing or dynamic IoT networks offer scalability and resilience, but they introduce unique challenges. So, when you consider these types of networks, there is no central authority, so without a single point of control, it can enforce consistent security policies. So each node must independently verify and secure data. So based on the topologies, here we can consider dynamic topologies. So adaptive networks change structure based on conditions. So it can consider features like load, latency, or failures, which makes it difficult to predict and monitor attack surfaces. So, based on the attacks, increased attack vendors are possible. So, more nodes and endpoints mean more potential entry point for attackers. So, especially in IOMT or smart city environments. So moving on to the trust management in decentralized systems, trust must be established cryptographically rather than through centralized overweight. So in point number 2, we are going to see about robustness and reliability. So cyber physical systems integrate computation, networking, and physical processes. So it uses CPS systems uh, to uh, to have some conditions which are unexpected, and it can be adaptable to subsystem failures. So we can use IOMT devices, autonomous vehicles, smart grids are also used in these types of systems. So these type of systems operate in real world environments, and there are so many types of environments. So we can have noisy environments. So sensor readings can be distorted by electromagnetic interference, temperature fluctuations, or mechanical wear. So there can be some uncertain conditions, for example, like external conditions like weather, human behavior, traffic. So that cannot be predicted. So we can consider that as uncertain principles. Uh, yeah. So sensor readings can be distorted. So we can have some noisy data, uncertain set of data, and we can also have dynamic data. For example, components may fail, so it can degrade or behave unexpectedly over time. So that we can consider as dynamic behavior, and based on robustness, withstanding the unexpected, that we call it as robustness. So we basically, you should know what is meant by robustness. That means the system can maintain functionality even when the conditions deviate from the normal. So, fault tolerance. The system continues to operate despite hardware or software faults. So that we call it as reliability. So given the uncertainty and noise in physical environments, these has to work properly. So noise resilience, algorithms filter out irrelevant or misleading data. For example, we can use algorithms like Kalman filters in sensor fusion, etc. And we can use some, so in case if subsystem fails, the system reduces performance rather than collapsing entirely. So this particular concept we call it as graceful degradation. So considering the example in a smart hospital, integrating biometric sensors from vendor A with a cloud analytics platform from vendor B might require redesigning the data ingestion pipeline. So this handles different encryption schemes and sampling rates. So we can think of so many properties here. So redesigning is a very important concept here. So to achieve seamless integration, engineers often need to re-architect the interfaces. So it defines new abstraction layers or use service-oriented architectures to decouple subsystems. So it can also use some middlewares, use protocol translators, and it can also have data format converters or message brokers. So some common protocols can be used here. So we can consider MQTT, OPC, etc. So to increase the standardized communication, we can adapt frameworks like DDS. So DDS is nothing but data distribution service or RESTful APIs to unify interactions. So integration of diverse subsystems can be mentioned. So we have integrating various hardware and software subsystems from different vendors. So often requires significant redesign of system interfaces. So redesigning of system interfaces is very common in IIoT. So strategic design principles are followed. To tame its complexity, robust systems often rely on modular design. So each subsystem is treated as a plug and play module with well-defined interfaces. So considering about the interoperability testing, so simulating real world interaction between components before deployment is possible. So vendor agnostic frameworks, so using some open standards and other constraints, it can isolate dependencies. So these are the fascinating principles and some interface standardization. So it's very much used in these types of systems. So next we are moving on to human machine interaction. So CPS systems are increasingly deployed in complex high stake environments. So the role of humans in CPS systems facilitates new assistance systems and multimodal user interfaces. So CPS systems are increasingly deployed in complex high stakes environments. So it can also be used in autonomous manufacturing, smart hospitals, or in intelligent transportation. So human remains critical decision makers here. So especially in edge cases or in some emergencies condition. So the goal is to integrate employees into a socio-technical system, so where operational safety and clear system status are also guaranteed. So human remains critical decision makers. So mission handle automation and optimization, but it needs to communicate clearly with the operators. So here in human and mission interaction, safety and trust depends on human intervention, human perception and mission precision, right? So this concept leads to the concept of socio-technical systems. So a system where human and technical components are co-designed to complement each other. So this is all about IIoT. So here you have learned about the closed loop systems. So it how it communicates with the other systems and what are the challenges in various systems. So thank you all. So we'll have one more topic in unit 1. So that topic I'll give you in the next video. So kindly look into it. So if you have any doubts, you can contact me. Thank you. Thank you all.